Good afternoon, class. We're continuing along with virtual memory today. Today's topics are page replacement, allocation of frames, and thrashing. And here once again are the chapter objectives. So remember, a system has a finite number of frames in general, which implies that process is going to have a finite number of frames, and presumably a process, as it executes, will eventually fill all of its frames with pages. And then if another page fault occurs, we have to select a page in one of those frames and swap it out to disk, and then bring in the page for which the fault was generated. Is due to the finite nature of memory, and as mentioned in the second bullet there, if the victim page, the page that's being swapped out, has been modified, then we do have to swap it out, write it out to disk. Otherwise, if it's not dirty, has not been written, we've only been reading data from it, then we actually don't have to swap it out to disk. So here's a small example. We have a physical memory with 8 frames, 2 of which are used by the operating system, and 2 running processes with the remaining 6 frames allocated evenly between them. So each process, you can see, requires 4 pages, so only 3 of those pages can be in memory. The program counter encounters a load M instruction, so it's loading memory word from this page, which you can see from the page table is not in memory. So we'll get a page fault. One of these pages will be selected and swapped out to disk, assuming that it's dirty, and then the needed page M will be swapped into a frame. So here are the steps. Locate the page that was the cause of the fault. Find a free frame. If the operating system is maintaining a pool of free frames, use the pool. Otherwise, select your victim page, and the victim page will be written to disk if it's dirty. So there's one disk operation. Bring the needed page into memory, into the freed up frame or the free frame, and then restart the instruction. So here is a second potential disk operation. So there are potentially two page transfers, 2 disk transfers that, as pointed to here, will increase the effective access time. So here's an illustration. Let's say we have a page fault for this page here, and this page is selected as the victim. So that page is swapped out. The valid bit is set to invalid. This page is brought in, and the invalid bit here set to valid, and then the instruction can be restarted. So the 2 questions here are: 1, how do we determine how many frames to allocate to each process? And then given that a process has a certain number of frames and therefore pages in memory, if a page fault occurs, how do we select the victim page? So the various page replacement algorithms can be evaluated using reference strings, which can be constructed from program traces, just looking at the page numbers. We don't, if you think about it for a second, we don't need to know the offsets within the pages, just the page numbers. And if you also think about it, if we had a repeated reference to page 3. Let's say rather than a single occurrence to page 3 here, there were a consecutive string of n references to 3. We can collapse them all down to the single reference because we will only potentially get a page fault on that first reference. None of the immediately following references to page 3 should generate page faults. This is the sort of behavior we would expect to see, that as we increase the number of frames allocated to a process, that the number of page faults for that process, the total number of page faults, would decrease. So the first page replacement algorithm we'll consider is FIFO. Here's a sample reference string, and as I counted it, there are 22 page references there. We're allocating 3 frames to the process. So initially, the process has no pages in memory. So the reference to page 7 generates a page fault. The reference to page 0 generates a page fault. And the reference to page 1 generates a page fault. The reference to page 2 generates a page fault, and at that point we have to invoke the page replacement algorithm. So process 7 was the first one in, so it's the first one out. This reference to page 0 doesn't generate a page fault because page 0 is in memory. Then the reference to page 3 will generate a page fault, and at that point we page out page 7, etc., etc., etc. And the result here is 15 total page faults. Now, there's something very curious about this reference string. If you run the FIFO algorithm on this string with 3 frames, you'll get a result of 9 page faults. If you run it with 4 frames, 1 additional frame, you'd expect no worse behavior, but it turns out that the number of page faults is 10, an increase of 1. This is known as Belady's anomaly. So here's a graph for that reference string and the number of page faults vertically and the number of frames allocated horizontally. So moving on to the optimal algorithm. In this algorithm, the page that is selected as the victim page is the one that won't be used furthest into the future. So in this example, when we get to this page fault and have to perform page replacement, we can see page 7 isn't being used for the longest amount of time. So that's the one that's selected as the victim. The only problem with this is, how do you know which page won't be used for the longest period of time? That's a bit of a problem. But since this is optimal, it can be used as the basis of comparison for other page replacement algorithms. So the optimal algorithm looks forward into time. The least recently used algorithm looks into the past, and it selects for replacement the page that hasn't been used for the longest amount of time. So looking, for example, at this page fault, we can see among pages 4, 3, and 2, 4 hasn't been used for the longest amount of time. So that's the one that's selected for replacement. For another example, page fault, consider this page fault here. And despite the fact that page 0 is older, it was used more recently. So the page that's selected as the victim page is page 1, which hasn't been used for the longest amount of time. The question here is, how do we track usage of the pages. So here are a couple ways that we could track which page was least recently used. One would be the timestamp, to keep a timestamp entry in the page table so that every time a page was referenced, its page table entry would be updated with the current time. And then when we had to select a victim page, we could scan through the page table looking for the entry with the oldest timestamp and choose that as the victim. Another idea would be to keep the page numbers in a stack with the oldest page deepest in the stack. And as you can read there, there are a number of updates that would need to be performed each time in order to update that stack. And as pointed out here, least recently used and optimal don't suffer from Belady's anomaly because they fall into the class of stack algorithms. A stack algorithm is a page replacement algorithm for which the set of pages in memory when you are working with n frames is a subset of the pages that are in memory when given n+1 frames to work with. So in other words, with stack algorithms, as you increase the number of frames, you have at least the same set of pages in memory, which implies, of course, that you can't have more page faults than you would with a lesser number of frames allocated. So this just illustrates the use of stack to track the page references. So here we have a page reference to 7, and you can see that it moves from deeper within the stack to the top of the stack. So in both these cases, it's page 4, which is the least recently used page. So because of the overhead that results from an actual implementation of least recently used, often approximations are used. So in one approximation, there's a reference bit in the page table, and as a page is referenced, that bit is set to 1. So that distinguishes, and every so often that bit is reset. So that gives us two classes of pages: those that have been referenced since the bit was reset, and those that haven't. But that's a fairly coarse level of granularity. We don't know the specific order, but we can replace any page whose reference bit is 0. Then we have the second chance algorithm, which uses what's known as clock replacement. So if so as summarized here, if the reference bit is a 0, replace the page immediately. If the reference bit is 1, it gets a second chance. It stays in memory, but we set its reference bit to 0, and then move on to the next page, waiting until we get to 1 for which the reference bit is 0. So we scan through the pages in a circular set, in a circular sequence within the page table. So here's an illustration. If this page is the next potential victim page and a page fault occurs, the reference bit is a 1, so we get the second chance, but you can see that the reference bit is reset to 0. Then we move on to the next potential victim page, but this one gets a second chance. So, but we set its reference bit to 0. The reference bit for this page is 0, so this will be the victim page. And you can imagine if all the reference bits are set to 1, then the clock algorithm will scan through the entire page table until it wraps back around and gets to the original next victim page, which will be the one that is chosen as the victim. So we can get an improvement if we also consider the dirty bit. The best page to replace is one that hasn't been referenced for a while and is clean, because we won't have to swap that page out. Next best is a page that hasn't been referenced but is dirty. It's not as good because we have to swap that page out, and then we move on to referenced pages. I'm going to skip these two algorithms. So here we see some optimizations, the first of which is to always maintain a pool of free frames in order to prevent the situation where we have a page fault, we first have to swap out a dirty page and then swap in the needed page, right, which will greatly increase the effective access time. So let's not swap pages out at page fault time, but instead, as the pool of free frames starts to decrease, then look for pages to evict and add to the free pool, and if necessary, track what pages are in those free frames, so that so that we can make use of them later if we actually need. All right, so that's this idea here, and the third idea is pay attention to the dirty frames, and when it's convenient, write them out to disk and reset the dirty bit. I'm going to skip this slide. All right, so now let's talk about how we allocate a number of frames to a process. For each architecture, there's an absolute minimum number of frames that are required. So consider a typical RISC processor executing a load word instruction. That instruction is potentially in one memory page, whereas the memory word being loaded into a register is potentially in a different memory page. Right, so that sets a minimum number of frames for a RISC processor to 2. Now let's extend that a little bit. Let's consider loading, for example, a double precision floating point number into a floating point register. So a double precision floating point number is 2 memory words. So that floating point number, one word could be in one page, and the second word could potentially be in a different page. So then, in addition to the third page that the instruction, the load double precision instruction could be in, that would set a minimum of 3 frames. And of course, the maximum number of frames we can allocate to a process is the total number of frames in the system. So we could either statically allocate a certain number of frames to each process, or dynamically allocate the number of frames and then use some sort of a priority function to determine, given the competition for frames among processes, how we allocate the frames among the processes. So here are a couple of fixed allocation schemes. First, to equally divide the number of free frames after accounting for the number of frames that the operating system needs equally allocate them to the processes, maintaining some as a free buffer pool, and then proportionally allocating frames according to the size of each of the running processes. So if we're using a priority allocation method, then if a process generates a page fault, the victim page could be one of its own pages, or it could be a page from a process with a lower priority. So in which case the process would be stealing a frame from a lower priority process. In global replacement, the victim can be chosen from any process's set of frames. In local replacement, the victim frame is one of the process that suffered the page faults frames. I'm going to skip this slide. So here's the definition of thrashing. A process doesn't use the CPU because it's constantly swapping pages in and out because of a large number of page faults due to not having enough pages. And you can imagine a system in which a long-term CPU scheduler has introduced too many processes into memory, so no process has a sufficient number of pages, so they're all thrashing, and the scheduler then notices, the long-term scheduler then notices low CPU utilization, so it throws in even more processes trying to get the CPU utilization increased, but much to its surprise, the CPU utilization continues to drop. So here's a graph illustrating the notion of thrashing. So as we increase the number of processes, CPU utilization goes up, but then we hit a knee in which no process has a sufficient number of page frames, so they all start thrashing, and the CPU utilization drops. In general, virtual memory works because of locality, and there are two types of locality, spatial locality and temporal locality. In spatial locality, the idea is that if one memory word is referenced, then a memory word close to that one. For example, if memory word 16 is accessed, with high probability memory word 17 will be accessed. That's spatial locality. Temporal locality suggests that if a memory word is accessed, then it will be accessed again in the near future. So processes operate in localities for over some period of time. They'll be referencing a particular set of pages from within all the pages that the process needs, and over time that locality can shift. So here's an illustration of that notion of locality. So time is this axis, and this is the process's memory space, and where you see marks, those are references to pages. So you can see over time the set of pages being referenced changes as the process's locality changes. This leads to the notion of the working set, the number of frames that a process needs to maintain its locality. So basically the idea with the working set model is that at certain periods of time, the operating system looks back over a certain set of page references, notes the number of unique references, and that number of unique references is the process's current working set. So you can see in this example, over this period, the working set was of size 4, and then as the locality changed and the access and the process's access pattern changed, the working set drops down to 2 frames. D here is the sum of all the working sets. So that's the total number of frames that are needed by the entire set of running processes. If that exceeds the amount of main memory, then we're thrashing, in which case some processes would have to be selected as victim processes, swapped out, and their frames reallocated among the remaining processes. So ideally, we would like to timestamp each page reference in order to determine the working set when we look over the last delta page references. But as we've spoke about with respect to the least recently used page replacement algorithm, that's a lot of overhead. So these timestamps can be simulated using an interval timer and the reference bits. So every time the interval timer interrupts, we copy all the reference bits into a number for each page, where that reference bit that we've copied moves into the most significant bit of that number, and all the other bits of the number are shifted right, with the least significant bit of the reference of this reference number being lost. So the greater number of such bits that we have, the more granular our timestamp can be. So 2 bits doesn't give us much granularity at all, and we could have a difficult time determining whether a particular page was within the delta or not. But if we, for this example, if we instead employed 10 bits and interrupted more frequently, that would give us a much more fine-grained result. So another idea, and as stated here, this is a more direct approach, is to simply control the page fault frequency for a process. So determine an upper bound for how many page faults per unit time, and a lower bound. If a process exceeds this upper bound, then allocate an additional frame or frames. If the process goes below this lower bound, then frames can be stolen from it. What this graph illustrates is the notion that as a process's working set or locality changes, its page fault rate will increase until its set of pages reflects the new locality. Then the page fault rate will decrease. Then that page fault rate will remain low while the process is operating within that particular locality. And then when the process's locality changes again, the page fault rate will increase and then decrease as that locality is in memory. This illustrates the notion that the delta for the working set, choosing the size of delta is important. If it's too large, then it'll encompass more than one locality. So a process would be allocated more frames than it needs. If delta is set to be too small, then the page fault rate will remain high because the process's locality working set won't be in memory. All right, so that completes this section.